Hey there, welcome back to the Introduction to Linear Algebra series. And I apologize for the delay in this video coming out. I have been busy with the deployment for a website I've been working on. And so we're back now with part 2 to our matrix representations video. And so just as a quick refresher of what we did last in the previous video was this, it was this change of basis problem where we had to find the matrix representation for the linear transformation. So our linear transformation was this, and the way we represented that was, well, we would take the first one, so 2, 2, 3, and we put it into our matrix with respect to our basis t, or with respect to this basis. So that's what happens when we put this into here. We're going to get this. Okay? And, oh, sorry, our linear transformation was this. Apologies. But yeah, when we take this and we plug this into that, then we're going to get this. And then if we plug in our second basis here, we're going to get this. And then when we merge them together to get our matrix, we get this. Okay, so hopefully that's all very familiar to you. And in this video, I wanted to continue matrix representation very quickly and get through the remaining examples and content that we had. And so let's find a matrix representation for a basis with respect to a basis for t squared plus t, t plus 1, and then t minus 1, and t minus 1. And this is all going to be p for the transformation from R2 to P2 since we're dealing with t squared, so that's quadratics. And our transformation is going to be for some vector AB in R2. Our transformation is going to be, we're going to take 4 of A, add that to B, and we're going to multiply that all by t squared plus 3AT plus 2A minus B. So this is our transformation here. And so let's try this for the standard basis. So if we take t of 1 and 0, and we use this here, what you should get is 4t squared plus 3t plus 2. And that is gonna give us 4 1/2 minus 3 by 2. Okay? And from there, let's use the second it's the second vector in our standard basis for R2. So 0, 1. And plug it in. Our similar reasoning is just going to yield us that t1 minus 1 t sorry, wrong. 1 t squared plus t plus minus 1 into t plus 1, and then plus 0 into t minus 1. And what that is going to give us is 1 minus 1, 0. And one thing we need to note is that this is with respect to d. So make sure to put d here. And so now we can say that our representation, we smush these two together in order. And we're going to get 4 1/2 minus 3 by 2. And then 1 minus 1, 0. And so that is with respect to d. And so that's how we do this type of problem. And it's very, very simple, and we've done it a lot in the previous video. And so hopefully we can skip a few more of those examples. Yeah. So in all technicality, there are two approaches to calculating a transformation of some vector, and we have a direct approach and indirect approach. And so the direct approach is, well, when you're given the transformation, so if I'm given that t of a b is going to equal some combination of a and then some combination of b, like 2a plus 3b, for example. If I have that, then what that is going to do, or what that's going to be, is that's going to be our direct approach. Okay? And that's going to yield us some vector in our other basis that we can represent using our other basis. The indirect approach is a bit different, where we're going to do it in a bit of a, it's not perfectly reversed, but it is where we're going to determine the coordinate representation for our for uh, for our vector first with respect to our other basis, and that's gonna give us out a different. That's gonna give us out our transformation. Okay, so let's look at this example again. This one. So if we use this, right, the direct approach, let's say we need to find, so we found the matrix representation, right? So let's say we have this vector here, 2 minus 3, and we need to we need to calculate it, okay, using both, for example, using both the direct and indirect approaches that we just learned. And so using the direct approach, well, we're going to get that 4 times 2 plus minus 3 all into t squared plus 3 times 2 times t plus 2 times 2 minus 3, and that's going to give us all 5t squared plus 6t plus 7. And this is perfectly okay for your small matrices. You can do this method, it works. But once you start getting bigger, I would recommend you want to use the indirect approach more. And so for the indirect approach, well, 2 and 3, that's going to equal, we're going to change our basis here. So if we're changing our basis, to the basis for the basis for R2, well, we can say that 2 times 1, 0, plus minus 3, 0, 1, and that's going to give us, it looks like the same thing. That's just because we're using the standard basis here. If they said without respect to a standard basis, if they said with respect to a non-standard basis, then you would be able to see clearly that this is just a bit different. Okay? And so now, since we know our matrix representation, what we can do is we can say, let's multiply our matrix representation, because it's simply just a matrix that you can multiply by in order to perform that transformation onto a vector of that belonging to that dimension. So let's say that we take our transformation that we had, right, and we're going to multiply it by this new matrix that we got here. New vector, sorry. And that's going to give us 5, 4, minus 3. Okay, and that's C. And so this and this, they don't look like they sort of work together just quite yet. But what you gotta do is you gotta remember to plug that into your transformation, or the equation for your transformation. So you can't forget to do that. So you're gonna get 5t squared plus t plus 4t plus 1, and then plus minus 3t minus 1. And that's gonna give you the same thing. 5t squared plus 6t plus 7. Okay, so at first glance, this might feel like a bit of a difficult way, but the main benefit of this is that if you have a massive vector here and you have a non-standard basis, what you can do is, instead of sort of plugging it all in to your transformation and having this super complicated long equation that, kind of doesn't make sense in a lot of ways, what you can do is instead first change your basis. So we stayed in the standard basis here, which is why our vector didn't change. But if it was a non-standard basis, then you would be getting a different vector here. And so once you change that vector, then what you could do, multiply it by your matrix representation that you calculated using the bases for the transformation. And so calculate your representation, multiply it by the vector that you got by changing the base, and then that'll give you this new vector that is the output of your transformation in terms of that new basis. And you just need to put that into your equation, and you're all good to go, pretty much. And so that's pretty useful. And so the direct approach is clearly quicker than what we did, but the indirect approach, it's entirely in terms of matrix and matrix operations, which is so much easier to understand and tangible. And I also feel that it might be a bit more uh, computable when you work with bigger and bigger. And so one final thought is that the subscript and superscript notation that we talked about on matrices and coordinate representations is really, really important in understanding, or rather keeping track of all our linear transformations. Because let's say we have a transformation like E v to w, and where v and w are vector spaces, right? And we have and we say w is going to be t, the output of t of v. Okay, and so vb is going to be our coordinate representation of v with respect to a b basis, and wc is going to be the coordinate representation of w with respect to the c basis. And so this approach is just going to give us a nice equation that's going to say, well, wc, that's going to equal abc vb. And this is going to be matrix A mapping an n tuple with respect to the b basis into an m tuple with respect to a c basis. And so the subscript on A must match the subscript on V, and the superscript on A must match the subscript on W. And so that's kind of the flow here, right? Because you're going like this and like this, kind of. And so every matrix represents a linear transformation, and that's something that you should keep in mind when you're doing these problems, and also understanding how matrices are taking vectors and mapping them to other vectors. And so that concludes linear transformations. And in the next video, we'll cover, I think, change of basis, and that'll be pretty useful for you in working in these problems, I think. And then, yeah, I'll see you in the next video.